Okay, so last time we talked about spectrochemical information. So we talk about radiation matter interaction, nature of spectrochemical analysis, from type of analysis, samples, spectrochemical phenomena, and we're going to, we could say, continue with the nature of these, what we call spectrochemical analysis. So the one that we're going to talk about today is reflection. Okay. So when we talk about reflection, this occurs when light bounces off the object. So when the sample is stimulated by application of an external electromagnetic radiations or several processes can happen other than absorption that we have discussed before. So one of them is what we call reflection. Okay? Bakit ayaw mag-ano ng akin? Walang. Yung writing pad ko. Ano? You're not connecting. There you go. Okay. So among these are reflection, refraction, and scattering. Okay. So the first thing that we're going to talk about is reflection. Okay. So when we're talking reflection, it is when light bounces off the object. So how much reflection depends upon how even, okay, the surface is. So if the surface is rough, we could say the light will scatter. But if the surface is smooth and flat, the light will bounce off it at equal angles. Okay, so this leads us to the so-called specular reflection and diffuse reflection. Okay, so I think the difference that we have here has something to do with what? Smooth versus rough surfaces. So if we're going to look at this reflection of smooth surfaces such as the mirrors or a calm body of water, this leads us to the so-called specular reflection. Okay. Now, if it's a reflection of rough surfaces such as clothing, paper, and the asphalt roadway, it leads us to this what we call diffuse reflection. So if we're going to look at the microscopic difference between these things, so this is the specular reflection compared to what we call diffuse reflection. So you could see how the light bounce off depends on the surface of the what we call where light is reflected. So the way reflection happens, so this is the incident, right? So it passes through, okay, and then it bounces off. So this is what we call the reflected light. So we have the angle of incidence and the angle of what we call reflection. Okay, and based on the laws of reflection, the angle of incidence is always equal to the angle of the reflection. So we expect this what? This angle here to be the same with the angle here. Okay, and the incident ray, reflected ray, and normal all lines in the same place. So you could see how these two types of reflection differed, okay, from one another. So another way to look at reflection as what? Change in the direction of a wave front at an interface between two media or two different media so that the wave front returns into the medium from which it originated. So the way we can look at it, if we have a mirror, okay, so this is the P and this is what we call the Q, and this is the normal one. So we have the angle here, okay. So if we're going to look at this, we could say one is the angle of the incidence, which is the one, P, that's your incident ray, and Q is your reflected ray. So this is the angle of what we call reflection. Now, if we're going to look like a monochromatic light hitting a flat surface at 90 degrees, so we could say I R over I0 is equals to N squared minus N1 squared over N squared plus N1 squared. So this one is the intensity of light, intensity of incident light, and this is the reflected intensity. Okay, so that's another way of what we call looking at this thing. Now, how about refraction? How is this different from the so-called reflection? Okay, so reflection, we can say bounces of light. So in the refraction, this is what? A change in the direction of a propagation of a wave when the wave passes from one medium into another. And usually they have what? Different densities. So there's an abrupt change in the direction or refraction of the beam is observed and changes its speed. So how do you think we look at refraction? So in reflection, bouncing of light, but in the refraction, how do you think we look at it? So let's say this is the incident light. Okay, this is air and this is glass. Is there any difference there? Do we see any difference there? Usually there's a difference there in the medium, right? So what usually happens? So we could say this is your incident light. So what will happen here? So this is the normal one. Ano mangyayari kapag nag-pass from air to what we call glass medium? So usually in one way or another, so this is the normal, there's a refraction that will happen. So like that one. And this is the angle of the, what we call, not really refraction, but refracted angle. So we could shoot this as this is 1, and this is what we call 2. And the way you do it is, so we could say refraction of the light is just passing from less dense to a more dense medium, and bending is towards the normal. Now, if the beam is passing through the other way, from the more dense to a less dense, bending away from the normal, of course. So we could say the light waves are refracted when crossing the boundary from one transparent medium into another, because the speed of the light is different in different media. Okay, so when the beam passes from a less dense to a more dense, the bending is toward to the normal, to the surface. But if it's from the more dense to a less dense, the bending is away from the normal. So the way you look at it is maybe like this. So you have here the angle of incidence and then the angle of partial reflection. So you could say when light passes through the medium, some of them are reflected and some of them are refracted. Okay. So here, this is the incident light. So Whatever the angle of the incident light is equals to the angle of the diffraction. But here, there is the angle of refraction. Okay? So, if we're going to look at this, so air and glass, okay? So, which one is denser? The glass, right? So, when the glass or when the light passes to the glass, so that's what, from a denser medium to a less denser medium, at a very special angle, the resulting, we could say, refracted angle is 90 degrees. And this special angle incident is called the critical angle of that medium. Okay? And usually, the one that have high index of refraction, or the so-called N, they have a low critical angle. So which do you think has what we call higher critical angle? Let's say diamond versus water. Although before we answer that question, we can look at the other way around, wherein when the light passes into a less dense medium with the angle of incidence greater than the critical angle, the light simply cannot exit the medium and is effectively trapped in the denser medium and reflects off the surface. So it does not pass through and refract, and we call it the total internal, what we call reflection. Okay? So some of them, like this one.
Yun. Actually, tama yung so dapat.
So if we're going to look at the one wherein you have what we call a critical angle of that medium. So you could see here, there's what refracted angle that's 90 degrees, like this one. But, okay, when the light passes into a less, what we call dense medium with the angle incidence greater than the critical medium, the light will not go out. Okay, so we have here the total internal, what we call reflection. But if we're going to look at this, so I asked the question, so which between the two do you think has the higher critical angle? Or not really critical angle, but index of refraction. This one. This is what we call an index of refraction, because it says here, substance that have higher index of refraction, they have low critical angle. So which do you think between the two here has a higher index of refraction? So try to imagine the water, okay, and then you pass a light through it, and then a diamond, you have a light through it. So which do you think would have a higher index of refraction? Or just say like a glass, because I think these diamond, they have like a glass like refraction index. Okay, so depending on how it passed through, you could see what happened there. So between the two, this one has a higher index of refraction. Okay, so usually it has an index of refraction at 2.42, okay, compared to water that is what, 1.33. And the critical angle that you have here for the diamond is what, 24.5 degree, and this one is what we call 49-degree angle. Okay, so that's just what we call looking at this one. But the one that we need to look at is the so-called internal, total internal reflection. Okay, because usually this is the basis of what? optical fibers. I'm not sure if you've read already these optical fibers. Are you familiar with optical fibers? Anyone? Is it only in the internet? Usually it's not only in the internet. In some of the instrumentation that we have, especially the portable one, okay, I don't know if you could see this thing. So the basis that they have in terms of this is what we call optical fibers. Okay, so you're going to look at this. I don't know if you could see here. So this is like a spectrometer, but this is just a very small one. So if you're going to look at that one, okay, so you may ask yourself, where's the light source coming from? Okay, so mostly, most of them, the light source is coming from their what we call optical fiber. Okay, so usually optical fiber depends on this total internal refraction. Okay, so the way that it do is whatever light source that they have there, it's going to reflect until they have this what we call enough light source. Yes, that's also the same principle that you have in this what we call internet. Okay, so like the cable right now, it just depends on what we call optical fiber. Now, if you're going to look at this refraction, the law that governs this is what? Anyone? Anong law yung nag-govern doon sa tinatawag nating refraction? Maybe you have learned it not in chemistry but in physics. Anyone? Have you heard this? Snell's law? Okay. So the one that governs, we could say, refraction, especially with respect to the radiation, is the so-called Snell's law. Okay. So, are you familiar with the formula of the Snell's law? Although we're not going to solve problems in this course, as I have promised you, I'm not going to give you calculation problem, okay? But if you're going to look at the Snell's law, this is just what? How do you put it? N1 sine theta 1 equals to N2 sine theta 2, right? And if you're going to look at this Snell's law, it's just stating that the ratio of the signs of the angle of incidence and reflections of a wave are constant when it passes between two given media. So that's what we call dictates this Snell's law. So it can also be written as what? B2 sine 1 equals to B1 sine theta 2, or sine theta 1 over sine theta 2 is just equals to B1 over B2, or N2 over N1. Okay. So if reflection is when you have the eye, how do we put the eye here? Like this, like having like this one for refraction, okay, it might be light and then going there. So that's, I think, the difference that you have for the two. Now, if we go back to this optical fiber, okay, so usually the way that we have this, just to simulate how refraction happen here. So when we have this multi-mode optical fiber, it will only propagate light that enters the fiber within a certain cone, known as the acceptance cone of the fiber. And the half angle of this cone is called the acceptance angle, okay, represented by this. So for full multi-mode fiber, the acceptance angle is determined only by the indices of the refraction. So you have here n sine theta max. So where you have the n is the refractive index of the medium light that is traveling before entering the fiber, and f is the refractive index of the fiber core, and n is the refractive index of this what we call cladding. Okay, so the cladding is some sort of what? The wall that happened here. So if you have what we call your light going through there, so that's what we're going to do is propagate the light through the fiber. Okay, so that's why if you have a fiber, we could say it's really full of information. Okay, so try to imagine when the internet is what? By the cable during the, I think, our time, and now it is run by optical fiber. Now, the last that we have is scattering. Okay, so when radiation is scattered, usually the interaction of the incoming radiation with the sample may be what? Elastic or inelastic. Okay, or we can look at this scattering of the radiation as what? The fraction of radiation transmitted at all angles from its original path. And you can say it either what? Elastic or inelastic. So when you have an elastic scattering, so the wavelength of the scattered radiation is the same as that of the source radiation. The intensity of this elastically scattered radiation is used to make measurement if you have nephelometry, turbidimetry, and particle sizing. So I'm not sure which one have you heard among the three terms here. Anyone? How is this nephelometry different from, which could say, turbidimetry? But all of them has something to do with elastic scattering. So particle sizing, you use the measure the size of the particle depending on how they scattered light. But nephelometry and turbidimetry, so where do you use this? Is this the first time you heard this term? Especially turbidimetry. So usually what do you expect them? You have like a turbid sample. Okay, so what you do is, if you have a turbid sample, maybe you pass through a light source and determine the scattered light. So what is the difference between the two, nephelometry and turbidimetry? So usually when we're talking about nephelometry, the intensity of the turbid, of the scattered light, okay, in the turbid solution is measured. Okay, now for the turbidimetry, the intensity of light transmitted through the sample is measured. Okay, so it's just like maybe what? Yung common term na inaano natin, absorbance versus transmittance, right? Absorbance is the amount of light, okay, that was we could say interact or absorbed by your sample, while transmittance is the amount of light that passed through the sample. So the same thing with nephelometry and turbidimetry. So nephelometry, the intensity of the scattered light is measured, okay, while in turbidimetry, the intensity of light transmitted through the sample is measured. And we also have this what? Scattering by molecules or aggregates of molecules with dimensions significantly smaller than the wavelength of the radiation, and that is called Rayleigh scattering. What is the classic example of Rayleigh scattering? Anyone? Wala kayong narinig about the classic example of Rayleigh scattering? Is this the first time for you to hear the reason why the sky is blue? Are you still there? Is this the first time for you to hear this? The explanation why the sky is blue is because of this Rayleigh scattering. Okay, so molecules or aggregates of molecules with dimensions significantly smaller than the wavelength of the radiation. So we could say the intensity is proportional to the inverse fourth power of the wavelength. Okay. Now, another thing we could say, oh God, di nga, natanong sa word exam. Another way where we could what we could look at the scattering by big molecules is how do we differentiate colloid from solution? Ano yung meron yung colloid na wala sa solution? And usually it happens because of the scattering by big molecules. Anyone? Have you heard this Tyndall effect? So Tyndall effect is being exhibited by the colloid. So one thing you know if it's a colloid is you pass, let's say you have the colloid sample, you try to pass a light through it, and if ever, okay, you will see that the light has like a pathway or a path length there. So that is your called Tyndall effect. So what it do, the colloidal molecules scattered the light that you have there. Solutions don't have that. Okay. So that's another phenomenon known of what we call the scattering. So if you look at the scattering, its instance is proportional to the inverse fourth power of the wavelength, the dimensions of the scattering particles, and the square of the polarizability of the particles. So an everyday manifestation of Rayleigh scattering is the blue color of the sky, which results from the scattering of the shorter wavelengths of the visible spectrum. So if you're going to look at this, there's a Rayleigh scattering from the air molecule. So the intensity is inverse of the fourth power of the wavelength. So if you're going to look at this, you only see the blue sky. That is what? 400 nanometer So 9.4 times greater as that of 700 nanometer for equal incident light. Now, in terms of this Tyndall effect, so the colloidal dimensions particles scattering can be seen by the naked eye, and it's used for measuring the particle size and the shape of the polymer molecule. Now, there are also, we could say, some other type of scattering. So we have this so-called me scattering or my scattering. Okay, so the Rayleigh scattering that you have is really spread out the direction of the incident light. Now for the me scattering, so with large particles, scattering can be different in different directions. So measurement of this type of scattered radiation are used to determine the size and shape of large molecules and colloidal particles. So maybe this is where you include your Tyndall effect. Okay, so me scattering is not strongly wavelength dependent and produces the almost white glare around the sun when a lot of particulate material is present in the air. I don't know if you observed that. Okay. And this usually scattering produces a pattern like an antenna lobe with a sharper and more intense forward lobe for larger particles. So this could be one type of me scattering. Now, if you have larger particles, so this is how it looks like. But the one that I am after with this type of scattering is the inelastic scattering, where the wavelength of the scattered radiation is different from that of the source radiation. So scattering in which the scattered photons have either a higher or lower photon energy, that's what we call the Raman scattering. Okay, so I don't know if you have heard the word Raman. Anyone? Have you heard this word? Raman. My students would call it ramen. Whenever they have the results, I think one student is always until the end, ramen, even if I corrected her that it is what we call a raman. Okay? So raman is based on what? The name of the person. I cannot pronounce the name, but I know the acronym is CB, as in curriculum vitae. Okay? So the way Raman spectroscopy, it uses inelastic scattering to produce a vibrational spectrum of sample molecules. And in this type of spectroscopic analysis, the intensity of the scattered radiation is recorded as a function of frequency shift of the incident radiation. And this intensity of the Raman peak is related to the concentration of light. Okay, so if you're going to look at this, this is how we could say the energy level that you have for the scattering. So as you could see, it's very different from infrared, although they complement one another. So IR together with Raman is a very powerful tool. Okay. One cannot replace the other because one can be applicable in one type of sample while the other one is not. So in IR, it's more on absorption. So light is absorbed. But in this, what we call Raman, so the way you look at this one, so it involves a quantized frequency changes. So these are the results of vibrational energy level transitions that occur in the molecule as a consequence of the polarization process. Okay, so if the amount of energy that absorbed is the same as the amount of energy that goes down, that is what? Rayleigh scattering. And usually it's strong. Okay, but if you're going to look at the amount of the energy, okay, is more than the amount of the energy that goes down. So there's a difference of this one. Okay, that is the Stock-Raman scattering. Now, if it's the other way around, you have this what we call anti-stock Raman scattering. So the way that we look at this one, so if the molecule, okay, in its ground state, upon interaction with the probe beam, the light can be absorbed and then re-emitted at a lower frequency since the energy from the light is channeled into the vibrational mode of the molecule. That is what we call the stock shifted Raman, this one. And usually this is how they look like, a little bit more powerful, okay, compared to the anti-stock. So anti-stock happens if the molecule is vibrationally excited state. When it interacts with the probe beam, the interaction can cause the molecule to give up its vibrational energy to the probe beam and drop to the ground state. So in this case, the scatter light is higher in frequency than the probe beam. So this is referred as this what we call anti-stock Raman scatter, and this is much less common compared to the stock scattering. Okay, so the most common occurrence of this light is the one that is absorbed and then re-emitted at the same frequency, and that is the Rayleigh. That's why the Rayleigh is what? Elastic, because they have the same amount of energy, okay, that is absorbed and re-emitted. But they're not the same. So this is what we call an elastic. So I don't know if you have heard this term also before. Did you hear the term before? Elastic and inelastic? Huh? Really? Kala ko IR lang doon. Another way of looking at elastic, I don't know if you recall your Chem, di ba, doon sa kinetic molecular theory. So when gas molecule hits one another, their collision is termed what? Elastic. There is no change in energy. That's why we could say in an elastic scattering, when the photon is absorbed by the particle and then emitted, there's no change in the energy. So that is Rayleigh scattering as the classic example. But with inelastic scattering, a photon is first absorbed by a particle and then emitted with a change in its energy. And that is what we call the Raman scattering. Now, between the two, which do you think is powerful? If I have a multiple choice question in your quiz, which do you think is more powerful? The Rayleigh scattering or the Raman scattering? Anyone? Alin sa tingin nyo yung powerful? Usually it's the Rayleigh, because what we do, if you have the Rayleigh, you cannot see the Raman. Now the question is, can you see the Raman in the presence of the Rayleigh? Yes, but you need some sort of what? A filter to cut off yung energy na na-emit ng Rayleigh. Okay? So I hope you're learning something. I don't know if this is the first time you encountered these terms that we're discussing, but another way of looking at this is polarization. So if we're going to look at the light, and it's what we call polarization, okay? So light can be represented as what? Ano ba usually yung light? It's a transverse electromagnetic wave. and made up mutually of perpendicularly fluctuating electric and magnetic field. Okay? So if you're going to look at this one, the left side here, so it shows the electric field in what? The XY plane, and the magnetic field in the XC plane. So there's a propagation towards the X direction, right? So this is your energy, and this is your magnetic field. So it propagates towards that one. Okay, so if we're going to look at it in terms of this one, so we could say this is what? Linearly polarized, when it contains waves that only fluctuate in one specific wave. Now, what happens if the light wave that is vibrating is more than in one plane? So we have this what? Unpolarized light. What do you think is the light emitted by the sun? What it is? Polarized or unpolarized light? Sige nga. Or di kaya yung lamp? Or di kaya yung punta tayo sa sinaunang kapanahunan, candlelight. How do you classify them? Polarized or unpolarized light? How about the others? So those terms that I mentioned, they are what we call unpolarized light. Okay? Such light waves are created by electric charges that vibrate in a variety of directions, thus creating an electric magnetic wave that vibrates in a variety of directions. So ang polarized line is just in one direction. Pero kapag nag-spread going here, propagate going here, propagate going here, propagate going anywhere, that is what we call unpolarized light. Okay? So an unpolarized light, they said, is harder or difficult to visualize, rather difficult to visualize the concept of the unpolarized light. But in general, it's helpful to picture unpolarized light, okay, as a wave that has an average of half its vibration. In a horizontal plane and half of its vibration in a vertical plane. So it goes anywhere. Okay. And usually we have used this polarizer as a material that allows only light with a specific angle of vibration to pass through. Okay. So if we're going to look at, we could say, this polarization of the radiation, this could be the interaction involved in the transmission that can be ascribed to a periodic polarization of the atomic and molecular species that make up the medium. So polarization is in the context means that the temporary deformation of the electron clouds associated with atoms or molecules that is brought about by the alternating electromagnetic field of the radiation. Okay. So if you have two polarizers, you set it in a series so that their optical axes are parallel, the light passes through both. However, if the axes are set up 90 degrees apart cross, the polarized light from the first is extinguished by the second. So nawawala na. Okay, I'm not sure if you know a polarimeter. Have you heard the term polarimeter? Saan nyo siya ginagamit? Sa organic chem ba? So usually, what do you use these what we call polarimeter? You try to measure optical activity, right? Okay. So if you're going to look at this polarimeter, you put your sample, and then you try to see if it can what? Rotate. Because you measure like the angle of the rotation of the molecule. So if you have the polarized light, it will either rotate clockwise or counterclockwise, and the amount it rotates indicates the angle of rotation. That's the D and the L thing. Okay. Now, in everyday life, what is an example of a polarizer? Anyone? Ginagamit natin to during summer. What's a classic example of a polarizer? Okay, the sunglasses. Sunglasses is a very good example of the polarizer. Okay, so the way you do what we call the polarization, you can do it by use of a Polaroid filter. So when you have a Polaroid filter, okay, what it do is it's able to polarize light because of the chemical composition of the filter. Okay, so yung sunglasses natin, parang filter lang yan. Ano yung pinifilter ng sunglasses natin? Anyone? Ito. Okay, so we just what we called filter the high energetic ultraviolet that we have in the sunlight. Okay, so the way that we look at this one, depende ba sa nabili? Yung iba pa lang nakakaano nung mata yung mga made in China. Unless yung iba yung mga ano ito, Ray-Ban, the really the good one, right? Pero pag Ray-Ban, malamang maano yung mata mo. Okay? But if you're going to look at the materials that you have there, the filter can be thought as having long chain molecules that are aligned within the filter of the same direction. So if you're going to look at this one, between the relationship between the long chain molecule orientation and the orientation of the polarization axis, so then when the molecules in the filter are aligned vertically, the polarization axis is horizontal. Now, when the molecules in the filter are aligned horizontally, the polarization axis is what we call vertical. Okay? So, as unpolarized light, strike, okay, the filter, what happened is the portion of the wave vibrating the vertical direction are absorbed by the filter. And the general rule is that the electromagnetic vibrations that are in direction parallel to the alignment of the molecules are absorbed. Okay? So, ganun yung ginagawa ng polarization by Polaroid filter. Now, there's also another way of doing what? Polarization. The so-called polarization by reflection. So, your unpolarized light, so any source of light, they can undergo polarization by reflection of non-metallic surfaces. Okay, so here you have unpolarized light. So if you pass it through a non-metallic surfaces, you can get this polarized reflected light. Okay, so the extent to which polarization happens depends on what? the angle at which the light approaches the surface and upon the material that the surface is made up of. Now, if you can do polarization by reflection, it's also possible that you can do polarization by refraction. Okay, so you see from this what we call diagram, the difference of reflection and refraction. So the way polarization by refraction happens, okay, when a beam of light passes from one material into another. So at the surface of the two materials, the path of the beam changes its direction, and the refracted beam usually acquires some sort of what? Degree of polarization, and most often the polarization occurs in a plane perpendicular to the surface. So we could say the light is split into beams, two beams upon entering the crystal. Okay, so if you're going to look at this, what we call object, looking through, let's say, a crystal, two images will be seen. Okay, so the two images are what? The results of this so-called double refraction of light. And both refracted light beams are polarized, one in the direction parallel to the surface and the other in the direction perpendicular to the surface. So since these two refracted rays are polarized with a perpendicular orientation, a polarizing filter can be used to completely block one of the images. Okay, so let's try to look at this one. So this is an effect of a polarizer on reflection from mud flat. So both of them has what? A polarizer. So what's the difference? Why do you see this scene and why do you see this one? So how do you think the rotation of the polarizer here? So we could say the rotation here is rotated to transmit reflection. Now by rotating 90-degree the polarizer here, almost all, okay, speculary reflected sunlight is black. Oops. Now how about this one? Which one uses filter? The left or the right picture? The one below. Maybe you can use this in what? Yun sa Facebook, di ba? Sabi nila pag may filter, mas maganda yung mukha mo kaysa sa unfiltered one. So which do you think here is the one used polarizing filter? The left or the right sa photo? Anyone? Ba't niya sabi sa right? Kasi mas maganda yung picture? Ganun ba yun? Yeah, the thing is the right one has the polarizing filter. The same thing as I told you, right? Yung kapag may filter, so sometimes pag walang filter, parang, siya ba yung kausap ko? and you're going to look that polarization has a lot of applications. Okay. So one applications that they have there is, we could say, in the industry, especially the one that has transparent plastics. So they use it to perform stress analysis tests. okay, on transparent plastic. So as light passes through its plastic, each color of visible light is polarized with its own orientation. And I think, are you familiar with 3D? Meron na yun sa Pilipinas, alam ko eh. Because I think way back, I'm not sure, 2018, when we watch, ano ba tawag dun? Yung Ant-Man, yung second Ant-Man. We watch it there with my son. Okay? Now, I don't know if you know the concept of the 3D. Di ba kailangan mo yung glass? A 3D glass, as they call it, right? And have you tried watching 3D scene without the glass? Ano yung makikita nyo? Have you experienced as you remove the 3D glass and then watch the scene? Is it clear? Hindi, di ba? Blurry. Okay? You need the glass to at least what we call experience that it is a 3D movies. Okay, so what you usually have in the 3D movies, there are actually two movies being shown at the same time through projectors. And the two movies are filmed from two slightly different camera angles. So that feels the three-dimensional stuff. And each individual movie is then projected from different sides of the audience onto a metal screen. So the movies are projected through a polarizing filter. Now, what the polarizing filter do is the movies are projected through a polarizing filter, and this polarizing filter used for the projector on the left may have its polarization axis aligned horizontally, while the polarizing filter used for the projection on the right would have its polarization axis aligned vertically. Okay, so consequently, there are what? Two different, slightly different movies being projected on the screen, and each movie is cast by light that is polarized with an orientation perpendicular to the other movie. So how you're going to witness this is you use the 3D glass. Okay. And in the 3D glass, you also have what? Two Polaroid filters, and each filter has different polarization axis, one that is horizontal and one that is vertical. Okay, so what's the result of this one? So if you have this, the one would filter the left eye, which is the movie that is projected from the right side, and the filters that is on the right eye, it is the movie that is projected from the left projector. And here you have the what we call perception. Okay, give the viewer the perception of depth. So parang nandoon ka talaga. I don't know if you have that feel. I think I felt it when ano yun, yung transformer. Halos mahilo ako kasi nandun ako sa harap. So I feel like nandun ako sa action. And I think my wife felt also dizzy watching, ano ba yun, yung Avatar. Okay? Kasi parang, ano na, sabi nga, kulang na lang lumabas yung amoy. But that is the explanation that why we have these 3D movies. Okay? So you just try to record them at different, we could say, camera at the different angle. So that's, we could say, the concept that we have for 3D. So it is a product of polarization. So I don't know if you know that. Okay? Or you just watch the normal one kasi mas mura kaysa sa 3D. How much is the difference of a 3D movie and a normal movie there? Usong-uso yan before pandemic eh. But after pandemic, hindi na kami masyadong nanonood. But that's how it is. Okay? So the difference here, I think, is around $5. A 3D versus a normal one. Now, how do we look it in terms of analysis of the real sample? So in qualitative analysis, the wavelength of the optical transitions are used to identify the presence of the chemical species. Okay, so usually we just look at a particular wavelength, and if we see that there's a absorbance there or an emission there, we could say that that sample or species might be present. But if we want the quantitative determination, we usually base it on the intensity, because here, if we only see it like this one, so if this is the wavelength, okay, we're not after the intensity of the absorbance. But in a quantitative one, what do we do? So this is the absorbance and this is the wavelength. But what's the difference if you want to do a quantity? Anyone? What's the difference of a quantitative determination and qualitative determination? So here we could say analysis of paint for lead, just answering the question, is lead present? And then determination of lead in paint, that's answering how much lead is present. So ano yung difference sa dalawa? What do you need to do? Additional things that you need to do. Anyone? How are you going to determine the concentration? Okay, you run a standard. You either run a calibration curve or standard. So samples are analyzed, but that concentration of the species are determined. So the way that you're going to do it is you run, okay, the species that you have, but with known concentration. Now you can have a single point comparison, or you can do a calibration curve. In single point comparison, you do what? Ratio and proportion. Either get the height or the area, whatever is what we call given. But that's how you analyze for the real samples. And let's say this one. So what can you say about your sample? All of them having the same what? It gave some peak in what? 253 here. And then this one. And then this one. So how do you know? So you look at any differences that you can. So what can you get from the sodium phosphate here? Is this enough to tell you that they're different? Okay. Is this enough to tell you that they're different? And also this, most probably yes. Or when you run them, so this what? Pure. So you can add one of them in your sample and then see what peak they will give up. But usually, whatever common peak that they have, they will go up. But there is one specific peak that usually you can assign to each of them. That's the harder part of analyzing real sample. But you just follow some protocol and you're able to do it. And the one day that you're going to do is what? Blank measurement required in nearly all spectrochemical techniques. Can we consider blank as water? Is water the blank in all analysis? Water ba lagi yung blank? The answer is no. Okay? The definition of the blank is everything except the analyte. So an ideal blank contains all the sample constituent except the analyte. So if you treat the sample, okay, with other reagent, the blank should also be treated. And the instrumental response from the blank is subtracted from that of the sample in order to compensate the effect of this concomitant. So you still remember concomitant from our lecture last time? So concomitance, we could say that's the matrix. That's everything that you can see in the sample, including the analyte. Now, an ideal blank, they should eliminate some type of interference effect due to the concomitants, but cannot compensate for concomitant species that affect the production and measurement of the analyte response. Okay? It is not easy to prepare an ideal blank, especially if your matrix is a little bit what? Complicated. Complex matrix. You don't know what they are. Okay? Now, in addition to that, you also have to take into consideration the container that you're going to use. They may give rise to additional interference effect due to the optical interaction of the electromagnetic radiation with the container form. So usually in molecular spectroscopy, you use what? Glass, quartz, and salt cells. So these are UV, these, fluorescent. Usually in fluorescence, you just use the quartz. In the UV, you just use the quartz. Glass and plastic, you can use it for visible. Now, salt cells are for the IR. Now, in atomic spectroscopy, you need a flame, a plasma, a heated chamber. So what it do, the hot gases can emit or absorb radiation, which can be potential source of interferences. Okay? And another thing that you're going to look is what? In doing analytical technique, so how to express spectrochemical information in a convenient manner so the analyte concentration data can readily be extracted, or the dependence of the results on chemical, physical, and instrumental variables can be summarized. So this is where we have what? The calibration data. Analytical chemists should always do this calibration data. So how do you do calibration data? So you prepare concentration of different, solutions of different concentration of your target analyte and then get the reading. So as much as possible, you want in your solutions to contain what we call the blanks, right? So you will see the difference if you didn't add any analyte on it. Sometimes you don't even need to do a set of data. Sometimes you can do the so-called standard addition. You can also use a calibration curve using standard addition. But is standard addition calibration curve useful or practical? Practical ba yung calibration curve that you do by doing standard addition? Yes or no? Because for me, why do a standard addition calibration curve when you just use standard addition? One blank, one known concentration, and then one is the sample. That's it. Why is it not practical to do standard addition calibration curve? Because the standard addition calibration curve, what do? All of them has your sample. And then you add what? Different concentration. So usually, what if your sample is limited? So the classic thing that you do is a standard addition wherein you have one that is blank, one that is your sample, and one that is your sample, and you add with known concentration. So whatever the reading that you have in these two, you subtract here. And whatever the reading that you have with this known concentration, you're going to determine the concentration of those that you have in your sample that is not added with standard. Okay, so you have here what? The total spectrochemical signal, the blank reference signal, and the analytical signal. So what's the difference with this? So when we have analytical signal, it's related to the concentration, analyte concentration, and other variables by calibration function. So you can define it as S signal equals to F as a function of the concentration, the wavelength, and temperature, time, and other variables. Now, the dependence of the calibration function on a specific variable is often given a particular name, like a plot of the analytical signal versus analyte concentration with all the other variables held constant. So that is what? A calibration curve, a working curve, or analytical curve. And then we also have this analytical function, okay, which is just the inverse of the calibration function. So CA equals to G with respect to S, and S is 10 to the negative fourth of the calibration function. And calibration function is just 10 to the 4 of the signal. So this provides a direct method for calculating the analyte concentration from the measured analytical signal for a given set of experimental conditions. And as much as possible, when you do this, you optimize, okay, the conditions or the parameters to get the maximum analyte signal. How do you do that, especially in AAS? The question, did you do AAS? How do you get the maximum signal if you're doing AAS? Di ba, meron kang claim doon, tapos parang may, ano bang tawag doon? XY, iaano mo yung gaano kalapit or kalayo yung light or flame source. Some with this, what we call modern instrument, they can do the optimization for you. But if you have the old one, the P-hit, so you have to manually play with it until you get the highest signal. Okay? So that is what we call optimization. Because you want, as much as possible, the signal that you have is the highest that you can get. So you can have the smallest or the lowest concentration that can be determined. Kaya minsan makikita mo, bakit ang taas ng signal ng instrument one day, tapos the next day, mababa. And you cannot interchange kung ano yung nakuha mo in one day with the one that you get the next day. That's the problem that I have with Raman. The students are always complaining to me that, well, how do you get a higher signal compared to us? I said, it's just on the alignment. So if you align the thing, okay, then you're sure on how to do it. So we also do it in the Raman. So how do we know if we have the maximum Raman. So we use a standard called toluene. So it has a signature peak around 1000. So whenever we align or maximize the condition, we try to get the highest peak that we can get. And after we get that, I think that's it. That's the one that we're going to what we call use up. Now, there are other stuff that you have here. Okay, I just tried to finish it so we can go to the next one. So signal to background ratio. Okay. So if we have the signal to background ratio, the thing that we want to do is as much as possible, the higher the signal and the lower the noise. You optimize it in most instruments. And then the relative standard deviation. So you need to have it in every analysis. And then the signal to noise ratio, the S over N. Okay, so signal to background. So yung, di ba, whenever we run in the IR, we do it before we put our sample, we run the background. And we want everything to be subtracted with the background. So any signal that we have there is really from the sample. Now, in the signal to noise ratio, you want it to be as higher compared to that one. Because how do you know this is just noise or signal coming from your sample? Okay. And the thing is, when you try to evaluate the criteria in spectrochemical analysis, you have to take this in consideration. The cost, the sample size, how simple it is, how portable, robustness. Okay, are you familiar with robustness in your Gen Chem? No, analytical. Ano yung robustness? Ano ibig sabihin ng robustness? Anyone? Kung magtatagal. Is it on the instrument or usually it's on the what? On the method, right? So you want your method to be what? Whatever the condition, okay, mobile phase composition, or here, yung signal to noise ratio, it will not be affected. Experience namin na nagalaw yung aming peak because we have a train station near the lab. So how robust is it? So every time we measure or do measurements, we usually run the toluene so we can see how far they are. So what we do is we align everything depending on the peak of the toluene, okay? Because the method is not really robust, but to prevent it from what we call the happening, the error coming from that, we usually run it with the known background. And then speed, sample prep, automation, interferences. So cost, you want it to be what? Low cost, okay? Now, depending on the sample size, what is the sample size that you're going to use? ML, liters, simplicity, portability. So how portable it is, okay? So what I'm trying to do, why I have this, because I learned, wala tayong ano dyan, di ba? Do we have spectro there? Spectropolarimeter? In UP Los Baños? Meron ba tayong spectropolarimeter? Sa nano, meron? So what I'm thinking, I was able to do it. I was able to get a 9,000 quote, but this yesterday, a teacher of my, a colleague of mine said, oh, maybe Elmer, this one is good. So I don't know if you see the price there. So maliit lang siya. Okay. So hopefully, I don't know. We will see. If ever I got successful in my application, you can see those instruments there. Okay. So sample prep. So usually you want less sample preparation. Automation, I think you can do it, but not as high tech as chromatography. Okay, and interference will always be a problem. So there should be a selective technique or a specific technique that's freedom from interference. Okay, and the other figure of merit, so this is just going back to your analytical chem, accurate. So how close the measured analyte concentration is to the true analyte concentration in the sample, precision, how reproducible they are, okay, sensitivity. So this is just the slope. You want the slope to be higher, okay? Signal over the concentration, the slope of the calibration curve or the change in analytical signal per unit change in the analyte concentration. And then you have the detection limit. So it should be 2 to 3 times the standard deviation of a blank measurement. LOQ, that's 10 times the LOD. And then the limit of linearity. So as you know, in the Beer's law, hindi lahat direct. What happened? Usually at high concentration, they start to do that. So the limit of linearity is just this portion that you have here. And then the dynamic range. So this is the range between LOQ and LOL. So to be useful, it should have a dynamic range of at least 2 orders of magnitude. Okay. So if you're going to look at this, so this is your detection limit. Okay. So it's how different your signal from the noise, for the minimum amount of concentration that you can generate a signal. And LOQ, that's 3 times the detection limit. And then the LOL, that's the limit of the detection. So you can have it from here going to that one. And then that's the dynamic range that you have. LOQ going to LOL. So that's what we have for today. And then I'll try to load the one that we have for Friday by tomorrow. And I will make available the quiz by tomorrow. Okay. And then the second one maybe by the weekend. Question. Tanong? You have learned anything? Or I just repeating what you have learned already in your instrumental analysis? May natutunan ba kayo? Raleigh scattering is what? Blue sky? No, maybe the what? The concept behind the so-called 3D movies. Why you use that 3D glass? That's why I'm enjoying teaching this one, because even I learned at least something new by teaching it. So question, kumpleto ba tayo lahat? Meron pa rin hindi nagpapakita eh. Kasi meron pang isa eh. Kaya hindi ko maano yung quiz eh.